The next big thing to usher in quantum physics was the photoelectric effect. Between 1888 and 1889, Heinrich Hertz, Wilhelm Hahlwachs, and Philipp Lenard performed experiments that showed light, and that's over here. Typically light is showed as these wavy arrows. That light incident upon certain polished metals, and here's a metal right here, would emit electrons. Metals, the electrons are not bound to any particular nucleus. They kind of float around kind of in a sea of electrons. So when this light is incident upon it, some of these electrons are knocked out. This is basically the photoelectric effect. What was interesting about the photoelectric effect, if the incident light over here had a frequency that was less than a certain cutoff frequency, there were no electrons emitted, no matter how bright the light was. If the frequency of the light was too small, nothing happened. Now, when the electrons were emitted, their number, the amount of electrons emitted, which you can count with a detector, were directly proportional to the intensity of the light. However, their energy did not depend on the light intensity. So the light could be very, very bright or very, very not bright, and all that would change would be the number of the electrons. The energy of the individual electrons would stay the same no matter how bright the light was. In addition, as soon as you hit this proper cutoff frequency, electrons started coming out. There was no delay. They came out right away. None of these properties could be explained with the classical wave theory of light. In order to explain this, Einstein took Planck's work, Max Planck, on the quantized nature of light. The deal was Planck only applied his quantum theory of light to light trapped within a cavity. That was the whole concept of the black body, where an object called a black body would absorb all the light on it and would not emit anything. The only way it would emit light is if it were heated up. So Planck said inside the cavity, quantum, no problem. Outside the cavity, Planck was still hoping that light was a wave. Einstein said no. Light energy comes in discrete packets of energy that were later named photons. And he used the energy described by Planck. So the energy of these photons was h, Planck's constant, times the frequency. So in Einstein's mind, light is a group of photons which act like particles, which again is what Newton had said centuries earlier. The quantized nature of light is important because an electron was only emitted when a single photon struck it. So you had to have one photon hitting one electron. All of the energy of that photon, which is why it's frequency dependent, was transmitted to the electron, freeing it from its orbit in the metallic substance and letting it leave. One more part to this equation. Because the electrons were bound to their atoms, and again in metals it's a very loose bond, they're actually flowing around through all the different nuclei, but there still is a bind there. The electrons are not free to leave the metal. So you needed a minimum amount of energy to free them. That's called the work function. This is going to be measured in joules. And once you get to that energy, then you can kick the electrons out. So the maximum kinetic energy of the electrons leaving the surface would be the energy delivered by the light photon, HF, and remember, one photon, one electron, minus the energy it takes that electron to fight its way out of the metal. Now, all of the observed properties of the photoelectric effect were explained by Einstein's work, every single one of them. And he received the Nobel Prize for that. That's the only Nobel Prize Einstein ever won. It was not for his work on relativity and E equals mc squared. It was for the photoelectric effect.